Warning: if you just want to do linear regression and are not interested in machine learning at all, you should probably
get out of here, for real?
Well, that was a joke. However, on a more serious note, standardization is not at all necessary to linear regression, and I will explain that in this video. In contrast, standardization is critical to most of the machine learning method. Hi everyone, this is Bill. Welcome to my channel. In this video, I will explain to you how standardization is done in machine learning and why it matters to most of the machine learning methods. In particular, I will show you how standardization affects k-nearest neighbor classification and LASSO regression. Standardization is a common technique that we use to make sure that all our x variables are of the same scale. We standardize x variables by removing their means and then divide them by their standard deviation. As a result, standardized variables have their means as 0 and their standard deviation as 1. Here is an example. There are two students named Sandra and Parvati, and we have their academic records, which include their SAT scores, ACT scores, and GPA. In case that you wonder why I used these two names, they are the girls in the introduction. Sandra was the one saying, "Get out of here for real," and Parvati was the girl smiling to Sandra. Anyways, before I digress even further, you can easily tell that their SAT, ACT, and GPA are all in very different scales. If you plot these three types of academic records, you can see that SAT scores have a way bigger scale than ACT scores and GPA. With the population mean and standard deviation of these three types of academic records, we are able to standardize the data for Sandra and Parvati. First, we minus the mean from their scores, and then we divide the difference by the corresponding standard deviation. After computing the results, we can see that the standardized scores are of much similar scales. We can plot the scores as a bar chart. This figure scale looks much more comparable than the previous bar chart that I have shown. The way to make sense of this standardized data is that, for example, we can say Sandra's SAT score is 1.3 population standard deviation away from the population mean, or Parvati's GPA is 0.02 population standard deviation below the population mean. So far, I have shown you how to do standardization. Now, I'm going to teach you why you should do standardization. But before that, I will show you something that is even more important: why you should not do standardization when it comes to linear regression. There are two steps in standardization: minusing the mean and dividing by the standard deviation. I'm going to refer to them as demean and scaling respectively. In this slide, I will show you that demean has no impact on the prediction of linear regression. When the data is unstandardized, we say that the model is y hat equals to the product of xi multiplied beta hat I plus b hat. When the data has its mean removed, we rewrite the model as y tilde equals to x1 minus x1 bar multiplied beta 1 tilde, so on and so forth. After expanding the terms, we see that the intercept terms have a fixed difference, whereas the beta terms are exactly the same. As a result, the predictions before and after demean are the same. As for scaling, we can see it in the form of matrix multiplication. Here, V is a diagonal matrix with dimension of p by p, and all the diagonal entries being the corresponding standard deviation of all p features. In other words, all the p x variables. Recall that for unstandardized case, beta hat is basically x transpose x take inverse x transpose y. Now, after scaling the data, we have beta tilde as xv transpose xv take the inverse xv transpose y. After matrix manipulation, we can see that beta tilde is basically the product of v inverse and beta hat. This is a very nice result, because if you multiply the scaled x variables with beta tilde, the product is the same as x beta hat. This tells you that the scaling doesn't affect linear regression prediction at all. Since both demean and scaling don't change linear regression prediction, we can confidently say that standardization is not necessary for linear regression. In contrast, when we do machine learning, things are vastly different. For example, standardization is critical for the successful implementation of k-nearest neighbor classification. When we conduct KNN, we find the k nearest neighbor based on Euclidean distance. In a diagram like this, we sum up the square of the difference in the x1 values and x2 values of 2 points, and then take square root to find the Euclidean distance between the 2 points. Obviously, the scale of x values matters a lot to the Euclidean distance. For example, in this diagram, the variation in x2 values are of bigger scale, so x2 will affect the Euclidean distance more. Another example is Sandra and Parvati's academic records. When we compute the Euclidean distance of their academic records, we observe that since SAT is on a much bigger scale than GPA, the Euclidean distance is dominated by the difference in their SAT scores. The difference in their GPA has almost zero impact on the Euclidean distance. This can be very problematic. Assume that we want to predict whether students can go into Tier 1 or Tier 2 schools based on their SAT scores and GPA. Here is an overview of the data. From the figure, we can see that students need to not only do well for SAT, but also obtain a high GPA in order to increase their chance of getting into Tier 1 schools. If we use unstandardized data and KNN method to predict whether a new batch of students can get into Tier 1 schools, the result looks like this. Apparently, since the SAT scores are of much bigger scale, it dominates the Euclidean distance. As a result, the KNN method predicts whether the new students get into Tier 1 or Tier 2 schools almost purely based on SAT scores. For those scoring below 1,380, KNN predicts them to go to the Tier 2 schools, and for those scoring above 1,380, KNN predicts them to go to Tier 1 schools. Such prediction is ridiculous as it basically tells us that GPA plays no role in determining which type of schools the students are going. Now, let's standardize the data and use KNN to predict again. The prediction is much more reasonable as it resembles the real data much better. I have uploaded the codes that generate this data and graphs in the description. If you want to try it by yourself, you can try it with R. Okay, let's move on to another machine learning method, LASSO and ridge regression, or in another word, the regularization method. Recall that the loss function or the minimization objective function of LASSO and ridge regression involves the absolute value of beta hat or the square of beta hat. Therefore, the magnitude of beta hat will shift the minimum point and hence affect the regression result. For example, assume a model that running speed of a person is 1.2 multiply his or her height in centimeter minus 1.6 multiply his or her weight in kilogram. If we change the unit of height from centimeter to meter, the height variable goes from a scale of 100 to 1. Therefore, the corresponding coefficient or the beta value increases from 1.2 to 120. Imagine that we do a LASSO or ridge regression for data related to this model and the beta value for height increases 100 times. Then LASSO and ridge will have a much greater incentive to shrink the beta value for height. I did a simulation in R and the code is in the description below. You can download it and run it by yourself to see the impact of scaling on LASSO. So when we run a linear regression for the data both before and after the scaling, the coefficient for height is exactly 100 times bigger when we scale down the data 100 times by changing the unit from centimeter to meter. The coefficient for weight, or in another word, beta hat for weight, stays the same. On the other hand, when we run LASSO regression with lambda equals to 0.2, the beta hat for height is no longer 100 times bigger, and the beta hat for weight also changes. Since standardization involves scaling of data, the scale of coefficient change, which leads to LASSO and ridge regularization shrinking the beta hat values by different extent. In the end, the prediction differs depending on whether the data is standardized or not. And that's it. You have finished learning standardization in machine learning. Remember to like this video and comment any questions of yours. And don't forget to subscribe to my channel. I'll see you the next time.